Welcome to AI Paper Podcasts, your shortcut to staying sharp on the latest in AI research. Today, we're diving into the brand new Qwen3 technical report.
That's right. And straight out of the gate, the big news seems to be Qwen3's unified brain.
Yeah, it handles both quick thinking and deep reasoning all in one model family. It's pretty neat.
Plus, they've introduced this smart thinking budget concept that optimizes how much brain power the model uses for different tasks, makes it more efficient.
Right, adaptive resource allocation. And get this, it now speaks 119 languages fluently. That's huge.
Seriously impressive. The early results are showing it often outperforms even bigger models in areas like coding, math, and AI agents.
So if you're looking to understand the next big thing in large language models, without slogging through the whole dense paper, you're definitely in the right place.
Exactly. For those of you deep in AI researchers, ML engineers, this paper is, it's significant, but yeah, it's a lot to digest.
So we're here to pull out the crucial bits, right? The architecture, the training tricks, those benchmark results.
Our goal is basically to give you a clear, digestible, but still comprehensive understanding of why Qwen3 is such a big deal.
Okay, let's unpack this unified brain idea. Qwen3 isn't just one model, it's a whole family, right?
Yeah, whole range. You've got the dense models, kind of like your standard LLM, scaling from a pretty small 0.6 billion parameters up to 32 billion.
And then there's the Moe side mixture of experts, including that flagship beast, the 235 billion parameter one.
Right, Qwen3 235B A22B. But the real game changer, like you said, seems to be this ability to just seamlessly switch between thinking and non-thinking modes within the same model.
Which is different from before, wasn't it? You needed separate models.
Precisely. Think back, you might have used something like Q32B for complex reasoning, and then, Qwen 2.5 chat for quicker responses. Qwen3 just merges these.
That implies a lot more flexibility for developers, I imagine. No need to manage separate deployments.
Exactly. It simplifies things. But how does it decide when to think hard and when to just answer?
Yeah, how does that work?
Okay, so that's where this thinking budget comes in. It's a really novel idea.
Okay.
Imagine giving the model a sort of computational allowance for each task.
Yeah.
Simple request, small budget,
right?
Complex problem.
Yeah.
You allocate a larger budget, letting it do more internal reasoning steps before spitting out the answer.
So you can actually control the trade-off between speed and depth.
Totally. It allows for this really fine-grained dynamic resource allocation, super useful for optimizing cost and performance depending on the specific application.
That sounds incredibly practical. Now, the report also mentions knowledge distillation, helping the smaller models punch above their weight. What's going on there?
Oh yeah, strong to weak distillation. Think of it like the smartest model in the family, the flagship, tutoring the smaller ones.
Okay.
It essentially transfers its knowledge and reasoning patterns.
Yeah.
So the key takeaway for you, if you're developing, is that you can get surprisingly powerful, smaller models without the massive compute cost of the giants.
Which opens doors for edge devices, maybe. Or just more efficient deployments.
Exactly. Resource-constrained environments become much more feasible.
And the benchmarks seem to back this up. The flagship, that 235B Moe, is apparently beating previous top open source models, even with fewer active parameters sometimes.
Absolutely. They threw a lot at it. 15 different benchmarks covering everything from general knowledge, reasoning, math, coding, all the way to multilingual stuff.
MMLU, GSM-8K, math, Evil Plus. The usual suspect.
Yeah, and more. And the flagship consistently outperforms strong contenders like DeepSeek V3 base, Llama 4 Maverick base, even their own Qwen 2.572B base.
But it's not just the scores, it's the efficiency, right?
That's a huge part of the story. The efficiency gains are really noteworthy.
What's really striking is that the Qwen3 Moe base models can match the dense ones using only about, a fifth of the activated parameters?
It is. It's a significant efficiency leap. It comes down to a few things working together.
Like the architecture.
Partly, yeah. They've refined the Moe architecture. Remember, Moe means multiple experts, only a few activate per token. This lets you have a huge total parameter count without the full cost.
So bigger potential capacity, lower running costs.
Basically. But also the data. They massively scaled up their pre-training data.
That 36 trillion token number.
Yeah, 36 trillion. Across 119 languages and dialects, that sheer scale and diversity just fuels better performance everywhere.
Okay, 36 trillion. How do you even get that much diverse data? That's mind-boggling.
They got creative. They actually fine-tuned their multimodal model, Qwen 2.5 VL, to pull text out of PDFs, like loads of them.
Leveraging vision capabilities for text extraction. Smart.
And they use their specialized models, the math encoder versions of Qwen 2.5, to generate high-quality synthetic data too. Think math problems, code snippets, Q&A.
So a mix of real-world extracted data and targeted synthetic data. And obviously, that huge multilingual push.
Definitely. A very comprehensive strategy.
And the pre-training itself wasn't just one big run, right? It was that 3-stage process. General, reasoning, long context. Why break it down?
It's about building capabilities methodically. Stage 1, the general stage, uses about 30 trillion tokens to build foundational language understanding and knowledge across all 119 languages. Standard 4K sequence length.
Laying the groundwork.
Exactly. Then stage 2, reasoning, uses a smaller but much higher quality dataset, around 5 trillion tokens focused on STEM, coding, logic, plus that synthetic data. Still 4K sequence length, but they tweak the learning rate decay to really embed reasoning skills.
Sharpening the focus.
Right. And finally, stage 3, long context. This uses hundreds of billions of tokens, but bumps the sequence length way up to 32K.
Okay, handling much longer inputs.
Yeah, they mix in longer texts and use techniques like yarn and dual chunk attention to stretch the model's effective context window even further during inference, like 4x. So each stage builds on the last.
A very structured approach. Okay, let's get into the architecture details. The dense models 0.6b up to 32b seems similar to Qwen 2.5.
The core ideas are there, yeah. Grouped query attention, GQA, Swidge LU activations, rotary positional embeddings, ROP, RMS norm.
But they made some tweaks.
A key one is removing the QKV bias they had in Qwen 2 and adding QK norm query key normalization in the attention mechanism.
Why the change?
They say it helps with training stability, especially as you scale up to these massive sizes. And yeah, the context length's got that big boost, up to 128K tokens for some.
Okay, and the Moe models, same basic building blocks, but with the expert layers.
Pretty much. Same foundation, but with that mixture of experts layer. They use 128 total experts, activating 8 per token.
A lot of experts.
Yeah, fine-grained. And interestingly, unlike their previous Moe, these Qwen3 ones have no shared experts between layers.
So each expert is fully distinct.
Seems so. And they use a global batch load balancing loss during training.
What's the goal of that?
To encourage the experts to actually specialize, So different experts handle different types of data or tasks better, makes the whole system more efficient and capable overall, like a team of specialists, not just one generalist.
Right, encourages division of labor. Okay, so that's pre-training and architecture, but then there's this whole post-training phase. What's the focus there?
2 main goals, really. First is thinking control, teaching the model to reason well and switch smoothly between thinking and non-thinking modes.
Getting that unified brain working properly.
Exactly. And the second goal is that strong to weak distillation we mentioned, making the smaller models inherit the smarts of the big ones.
And the process differs for the big flagship models versus the smaller ones.
It does. The flagships go through a pretty intensive 4-stage process for that thinking control.
Stage 1 being long cold start. Sounds like getting the reasoning basics down.
That's the idea. They used a high-quality data set of math, code, logic problems with verified step-by-step solutions chain of thought.
Carefully filtered data.
Very carefully. Filtered using Qwen 2.5 instruct in humans. The goal wasn't peak performance yet, just embedding those core reasoning patterns efficiently with minimal data, setting the foundation.
Makes sense. Then stage 2, reasoning RL. Using reinforcement learning for better reasoning.
Yep. They use a separate set of challenging problems and apply an RL algorithm called GRPO. Big batch sizes, lots of simulation rollouts. Basically intensely training the model to get better at solving these tough reasoning tasks.
Trying different approaches and reinforcing the good ones?
Kind of. Balancing exploration and exploitation. And it worked. They saw huge gains, like on that AIM math competition benchmark, the score jumped massively.
Wow, from 70.1 to 85.1, that's significant. Okay, stage 3, thinking mode fusion, merging the modes.
Exactly. Now they integrate the non-thinking ability. They continue fine-tuning, but use a mix of thinking data with detailed reasoning and non-thinking data, direct answers to diverse tasks.
And they use the special chat template flags. Think and no think.
Right, to explicitly guide the model.
Yeah.
But an interesting side effect was the model started handling intermediate cases partial thinking, which paves the way for that thinking budget control.
So the budget control isn't just tacked on, it emerges from this fusion process.
Seems to be linked, yeah. And finally, stage 4 for the flagships. General RL.
Broadening the capabilities.
Pretty much. making the model more robust and useful across tons of scenarios. They use a complex reward system covering over 20 task types, instruction following, format adherence, alignment, agent abilities, even RV.
Using different kinds of rewards.
Yeah.
Rule-based, model-based.
Yeah, a mix, including using a separate trained reward model to judge quality based on human preferences, even without a single right answer, really aligning it with user expectations.
That sounds incredibly thorough for the big models, but the smaller ones use the distillation approach instead.
Right, the 5 smaller dense models and the 30B Moe use the strong to weak distillation. 2 main phases there.
Okay.
First, off-policy distillation. Basically, train the student model using the teacher model's outputs, both thinking and non-thinking, to mimic its behavior. Gets the basics down.
Learning by example.
Then, on-policy distillation. The student model generates its own responses, and then its internal probabilities are tweaked to match the teacher model's probabilities for that same input. It's about aligning the internal reasoning process.
And this was much faster.
Way faster, like 110th the GPU hours of the 4-stage process, according to their preliminary results. Big efficiency win for the smaller models.
And did the post-training evaluations confirm all this worked? How did they measure success?
They used a ton of automatic benchmarks again, specifically testing both thinking and non-thinking modes across general knowledge, alignment, math reasoning, coding agents, and multilingual tasks.
Benchmarks like MMLU Redux, Arena Hard, Math 500, Live Code Bench.
All those and more. The key finding: the flagship Qwen3 235B A22B showed state-of-the-art performance overall among open-source models. It surpassed models like DeepSeek R1 and V3. It was really competitive with closed-source giants like O1, Gemini 2.5 Pro, even GPT-4o in some areas.
Wow, that's a strong claim for an open model.
It is. And the Qwen3 32B also performed really well, beating their previous reasoning model and holding its own against comparable closed models.
And the distilled lightweight models.
Consistently outperformed other open-source models of similar or even larger sizes. So that strong-to-weak distillation really paid off. Validation confirmed.
The paper also dug into the effectiveness of the thinking budget specifically, didn't it?
Yeah, they showed experiments where increasing the thinking budget led to smooth, scalable performance gains on math, coding, and STEM tasks. More budget, better reasoning. Pretty clear correlation.
So it actually works as intended, giving you that controllable depth.
Seems so. And they expect it might be even more beneficial with really long outputs beyond 32K.
And that on-policy distillation for the smaller models, not just faster, but better results sometimes.
That was another interesting finding. Compared to RL from the same starting point, distillation apparently gave significantly better performance on math and code tasks, using only about 110th the compute. It also seemed to help exploration, improving scores on some benchmarks.
So a win-win. Faster and potentially better for certain tasks.
Looks like it. And finally, they talked about the impact of those last 2 flagship stages, thinking mode fusion and general RL.
Right, balancing reasoning with general usefulness.
Exactly. Stage 3, fusion, was key for integrating the non-thinking mode and improving general instruction following even within the thinking mode. Stage 4, general RL, then boosted capabilities across both modes and made sure the mode switching, think, no, think, was accurate.
Were there any trade-offs?
They noted some slight dips on highly specialized reasoning tasks like AIM after the general RL stage, but the trade-off was much better overall versatility, instruction following, and format adherence, making it a better all-around assistant.
Okay, makes sense. You optimize for breadth sometimes. They also touched on long context and multilingual abilities in the appendix.
Yeah, briefly. On the ruler benchmark for long context, the non-thinking Qwen3 models generally outperform similar Qwen 2.5 models. Thinking mode saw a slight dip, maybe because pure retrieval doesn't benefit much from deep reasoning steps.
And multilingual.
They showed detailed scores across a dozen languages demonstrating competitive performance. And on the Bella Bella benchmark covering 80 languages, Qwen3 was comparable to similar Gemma models and better than Qwen 2.5. So that massive multilingual pre-training data paid off.
It really seems like Qwen3 is a significant step forward for open source LLMs. That unified thinking, non-thinking framework and the thinking budget are genuinely innovative.
Absolutely. The technical report is packed with detail, a must-read if you're really digging into this stuff. The benchmark results are hard to ignore, especially in tough areas like coding and math.
Shows real potential for all sorts of applications. And that expanded multilingual support just opens it up globally.
It really broadens the reach.
So we definitely encourage you, our listeners, to check out the Qwen3 paper and the models themselves. They're publicly available. Think about how these advancements might impact your own work.
Now, what experiments could you run with a model that has this kind of built-in thinking control? What new possibilities does that unlock for your projects?
This deep dive is really just scratching the surface. The Qwen team mentioned future work on scaling data even further, refining the architecture, improving RL.
It sounds like they're not stopping here. We'll definitely be keeping an eye on future developments right here on AI Paper Podcasts. Perhaps the biggest question this leaves us with is, how will this ability to explicitly control the depth of reasoning change how we design and interact with AI systems in the future?
A great question to ponder. Thanks for joining us for this deep dive into Qwen3. We'll catch you in the next episode.